Well, and on the topic of the classic statistics, when you're showing your original plots and showing the scatter plots, you weren't able to actually observe a trend. Were all other like frac parameters actually considered? And if not, then could you comment about why this actually proves classic statistic cannot find the pattern in the data set you're showing?
Well, what I did essentially was, yes, I used every single parameter that I had, and I sliced it and diced it in every possible way. And I know, people are using these softwares right now that can handle much larger number of data than Excel can, and it provides a lot of visualization. You can do as much as that as you want, and what I'm submitting to you is at least I was not able to get any meaningful trend out of that, to be able to use it in order to make conclusions whereby it can be used in designing new frac jobs. And keep one thing in mind, the idea is to take guesswork and human bias out of that. And statistics, one of the problems with statistics is, conventional statistics, one of the main problems with classical statistics is that although it works with data, but it does bring in human bias in it to begin with. In other words, when you do statistics, you always start with a predetermined functional shape. You do regression, you do linear regression. The word linear has a meaning, right? When you do nonlinear regression, then you have to identify, is it polynomial? What degree? Is it power law or logarithmic? So you always start with a preconceived notion of the shape of what you're trying to find, whether your hypothesis is correct or not. And by doing that, you shoot yourself in the foot, and you limit yourself in things you can do. Whereby when you do data mining and AI and advanced data-driven analytics, although you use the statistics a lot, but you never start with a preconceived notion of functional form. You let the data tell you what it's supposed to have in terms of information in it, rather than you try to fit it to a preconceived notion of how shape of these functions should be. So that is the reason my recommendation to those who are going in this direction is, I'm not saying you don't use statistics traditional, but don't think that is going to solve all your problem. It's a very good starting point, but it's not going to give you what you're looking for.
All right, and then can this methodology for reservoir modeling be used to find the most influential parameters on an EUR basis for a given asset, for example?
Absolutely. As long as the data exists, you can use this to find out. There is another set of analysis that we have performed that I didn't show here, and we're not ready to present it yet. We're going through the legal process of patenting it before we show them. But there we use this supervised mapping technologies in order to specifically learn the contribution, very explicitly identify contribution of different parameters in success or failure of certain jobs. And and that technology we developed it actually for shale right now, but the same way that others were applied to shale, that can also be applied to EOR or any other operation, as long as you have data that you want to analyze.
Right, and in a lot of people's experience, they say use 3 to 5 parameters that account for essentially all the production variation. And can you confirm this? Or
no,
how many parameters would you look at?
Actually, we confirm that it's not correct based on the data that we have seen in shale. That notion is incorrect. We have used as little as 10 and as many as 25 to 30 to be, and again, it all has to do with the complexity, the size of the field, the number of wells, the history of that you are trying to model. Again, keep in mind, I keep saying that this is data-driven analytics, but don't forget we're reservoir engineer, we're production engineer. So diffusivity equation, Darcy's law, anything that you've learned as a reservoir production engineer is actually going to help you do this. So just look at the issue of fluid flow through porous media. It is a fact that as you increase the size in space, then you have a lot more samples to work with. You get better understanding of the physics as you increase the time that this operation is ongoing. So again, everything is happening in time and space. So it is a function of that. The higher, the larger the space, the longer the time, the better is your chances of finding patterns and building models that can be validated. And the notion that everything's being controlled by one or two or three parameters, I think is gross oversimplification of a very complex problem.
All right. I actually had a follow-up from a previous one. They wanted me to specifically ask the concept of grouping wells based on performance indicators being applied to conventional reservoirs modeling.
Yes. We have done that very successfully to conventional reservoir modeling as well.
Okay. And then applying fuzzy logic to categorize well behavior. Which parameters you emphasize on most?
To categorize, the only thing we emphasize on is production. When you go, for example, to conventional, we do this based on water cut, for example. A poor well is the one that cuts a lot of water. And a good well is when you, so it has to do with production, but based on what is it that your objective, it could be oil production, it could be GOR, it could be water cut, and it could be anything that comes out of the well. That is going to be, you categorize things based on based on your outcome. And then you use that outcome. That's usually the data you have, and you have reasonably good measurement of it as well. So you categorize it based on that, and then you have a bunch of parameters, such as well parameters, reservoir parameters, workover parameters, completion parameters, and then you try to relate these parameters to these outcomes that you trying to figure out and identify patterns with.
All right. There's also a couple of questions regarding just your definition of hard and soft data. If you could go into that a little bit more, and specifically, some of what you referred to as hard data is still, a lot of people think of it as being interpretive still, so it isn't necessarily fully hard. It can be quite soft as well. There's, let's see here. I didn't see any specific examples that they gave in terms of just the data being interpretive in what you classified as hard data.
Yeah, I would be interested to know which one it is. Because, for example, initial shut-in pressure is something you measure. Breakdown pressure is something you measure. I do understand some of these may not be available to you at the beginning, but nevertheless you can analyze them and figure out the characteristics of the reservoir. They become reservoir characteristics issue. You may not use them as inputs, but nevertheless you want to analyze them. But things such as amount of fluid, injection rate, amount of proppant, I think there's very little interpretations associated with those. Soft data is everything that you interpret, fracture half length, fracture height, fracture conductivity, or stimulated reservoir volume, things that we use normally in our reservoir numerical modeling. None of them are something we really measure in the field. Nobody can measure fracture half length in shale. I don't even believe such a thing even exists. It's a figment of our imagination. Fracture goes where fracture wants, and it doesn't have a half-length. It doesn't look anything like what some of these softwares make us believe to look like. They go anywhere they want. The most recent work that's being done, they're using discrete fracture networks and connecting them to induced fracture, and then you will see in them they're trying to create this fractal type of induced fracture propagation, which seems to be more closer to what's happening than these very well-behaved systems that people use. But I think even them use complete statistics, because nobody knows away from the wellbore what the natural fracture looks like. It's all statistics.
Right, so I think just to generalize what you're saying, I would take it as being hard data is, like you said, data that you actually are specifically measuring.
Correct.
Potentially they might have been referring to, you could take that and then interpret what the occurrence or how that data actually would then interacted with the reservoir, and that would be more of an interpretive side, which you're trying to avoid.
Mm-hmm. Yes, exactly.
All right, and I think we're probably going to be looking just maybe one last question here, given our timing, and I'll give you, it's kind of a simple one, but it could be kind of a, could be so long answer is, what is the greatest advantage of your workflow?
Well, the greatest advantage of it is it's here today. It can be used today, and it can the greatest advantage I see immediately is that it provides full field analysis. It deals with all the wells in when it comes to modeling. It's not single well; it's for all the wells. That's number one, and so provides a global asset-wide view of what you're doing. And then it is fact-based. Human bias goes out of the door. So in other words, you listen to the reality and you let the facts speak instead of our interpretation of them. And sometimes these facts confirm some of the things that we believe. Those are fantastic. And sometimes, they don't. And we have to be able to accept it and then try to figure out why and see if that is actually the case and learn from it. So I see them being fact-based and being full field as two most important issues for them.